Hello, I'm David Carr of the University of Maryland Human-Computer Interaction Laboratory. This video demonstrates animated specifications using interaction object graphs, or IOGs. IOGs are a method for specifying graphical widgets. Here we see an IOG specification for a secure switch. IOGs are an extension of David Harrell's state charts adapted to widget specifications. IOGs add data modeling for widget attributes and a special type of state to represent changes in the display. Here's a secure switch we've specified. It's secure in the sense that the operator must slide the switch from one side to the other in order to operate it. Notice when I press the mouse button, Roquefort will replace the cursor. This is simply a visual cue to let you know when the mouse button is pressed. The switch is divided into three regions: on, mid, and off. To toggle the switch, the user must point at the region for the current state, press the mouse button, drag through mid into off, and release the mouse button while still in off. Simply clicking on one side will not cause the switch to change. Dragging properly, but releasing outside of the region will not change it either. The secure switch was designed for a touchscreen to prevent accidental changes. This program demonstrates animating IOG specifications. Here's the specification and the operating widget. Eventually, a diagram editor will directly translate the IOG into code. Currently, this is done manually. We use a C++ class library that implements the IOG abstractions. The class library directly supports the animation. Animation helps the designer debug the specification by locating problem areas while the widget is running. The specification consists of 5 display states. Display state activation initiates a change in widget visual appearance. Display states are drawn as rectangles showing how the widget will look as the states become active. Display states are also atomic states, and atomic states represent the computer waiting for user input. The display states are split into 2 groups: operating states and static states. Each is contained in an XOR metastate. XOR metastates are drawn as rounded rectangles containing states. When an XOR metastate is active, exactly one of its child states is active. This gives sequential execution. In addition, any arc from a metastate applies to its children. The entire widget is an AND metastate. AND metastates are represented by a rectangle subdivided by dashed lines. Each subdivision is either an XOR metastate or contains a single data node. When an AND metastate is active, all of its children are active. This gives parallel execution. This is a data node. Data nodes represent widget attributes, in this case whether the switch is off or on. Finally, these black circles are start states. They are the first state active when their parent state is activated. Arcs connect states. There are 2 different types: control arcs and data arcs. Control arcs link states and represent the effects of user actions and system status. They are labeled with a precondition. Preconditions are written in a notation similar to Siochi, Hartson, and Hicks's user action notation. If this state is active and the precondition is true, then this state will become active and the original state will become inactive. An arc through a circle D is a data arc. They represent changes to the widget attributes. In addition to a precondition, data arcs are labeled with value used to update the attribute. For instance, on and off. Finally, the data arc leaving the widget means that the value of the switch is externally readable. To manipulate the switch, first if we're pointing in the off region and we press the mouse down, this arc will be taken and this state becomes active. Then as we go moving the mouse in the middle, this state becomes active. And finally, as the mouse is moved in the on region, this state becomes active. Now, releasing the mouse will cause 2 things to happen. In, on, and mouse up is true, so on will be copied into switch, and also the mouse up arc will be taken because it's inherited by all of these states, and this state will be activated. Once that's activated, the test will be made, and switch equals on is true, and this state will become active. In order for the operator to change his mind and cancel turning the switch off, it operates as follows. First he goes into the on area and presses the mouse. Then he would move into the middle and then to off. Not changing his mind, he would move outside of the off region. Now when he releases the mouse, since we're not in off, this condition will be false and there'll be no change in the value switch. It will remain on. However, releasing the mouse here, this arc will be taken, this state started, and this test will again be true. The switch will be on, and so it will return to the on position. The next widget is a simple horizontal slider. This widget illustrates how data arcs can be used to specify dynamic movement. For space reasons, only the behavior of the slider indicator is shown. The attribute location is the position of the slider indicator. Location is determined by the data arc from value. C change is an equation that computes the x-coordinate of the location. Whenever value changes, this data arc changes the location. Value can be changed externally via this data arc or by the user via this data arc. When this state is active, changes in the mouse position will cause C drag to update the value. To operate the horizontal slider, first the user points at the indicator and presses the mouse down. This activates the dragging state. Now as the user moves the mouse, the slider indicator tracks and the slider value changes. When the user releases the mouse, it snaps back into the idle state here and sets the new slider value. This slider has a feature that allows the user to change his mind and restore the old value. When he presses the mouse down inside the indicator, value is written into this attribute old value. Now it tracks as normally. When he leaves this area here, which is the active area, then he goes into a canceling state. Now releasing the button will copy old value into value and the slider will snap back. The last widget is a two-level slider. This slider permits the user to select each element from a range that is greater than the number of pixels used by the slider. For example, this slider has a range from 0 to 1,000, but it only occupies about 300 pixels on the screen. Thus, each movement of the mouse 1 pixel would move the slider about 3 or 4 counts in its range. The slide area is divided vertically. The upper half is the coarse area. Starting the slider in this area causes the slider to jump 3 or 4 counts for each pixel of mouse movement. The lower half is the fine area. Fine operation moves the slider 1 count for each mouse pixel. While this specification looks much more complicated than the last, there are only 2 modifications. First, the dragging state has been replaced by this XOR metastate. This state handles a coarse and fine modes with the 2 different dragging states. This is a history state. It remembers which state was previously active. When the IOG returns from the canceling state, the previous active mode is reactivated. The second change is that this arc implements a jump to value shortcut. Clicking in the slide area causes the slider to jump to the mouse location. Now let's set the slider to 800. First we'll move the mouse over to about 800 and click down in the coarse area. Then we'll drag toward 800, we'll get to 799. Releasing the mouse, we'll go into the fine area and go to 800. You've seen the animation of IOGs while the widget they specify is operated. Future work includes developing a visual editor and debugger for IOG specifications, adding memory of arcs traversed and states activated to show test coverage, extending the technique to user interfaces and possibly to illustrate the execution of any system with respect to its visual specification. Thank you.